Hello everyone and welcome to the assignment 2 presentation of our group presented by Mason Shipton, Zain Syed, and Josiah Jahoy Kemyap. So for this presentation, we're going to consider this system x dot equals x times x squared minus 2x plus 1 minus a, where x is an element of all real numbers and a is a real parameter. We're given three main tasks, which is to sketch all qualitatively different phase portraits that occur as a is varied, indicating the range of a for which they are valid. We're given the task of determining all the values of the parameter a at which bifurcations occur, and we classify them. And we're given the task of sketching the bifurcation diagram after completing a and b, of course. So let's cover part A first. To sketch all qualitatively different phase portraits, we first need to solve for the equilibrium solutions of x dot. So let's say x dot is some function of x, right? So to do this, to find the equilibrium solutions, we need to find f of x equals 0 to find the equilibrium solutions. Okay, so given this, we just have to find the solutions where it's equal 0. The easiest one would be where x equals 0. As you can see, it's factored right out there. And the second one is this thick equation. Notice that this part, x squared minus 2x plus 1, that's a perfect square. And we can rewrite it in the form of x minus 1 squared minus a. Okay, and now we equate that to 0. So from this, we can kind of split it off. We have first x1 equals 0. Then we have a second part of the solution, 1 plus square root of a. We get 1. And the other part is x cubed, 1 minus square root of a. This is just difference of squares, right? This one, imagine this is the first part of the difference of squares. This is the second part, the a. I'm not sure if you can see this. But x minus 1 is the first part of your difference of squares, and a is just the constant part. Okay, so that's how we arrived with x2 and x3. So x2 and 3 are real when a is greater than equals 0. So to find the stability of the equilibrium solutions for different ranges of a, we're going to need to find the derivative of f of x. So we solved it. F prime of x is equal to 3x squared minus 4x plus 1 minus a. Now, I'm going to focus on the part where we solve for x1 equals 0 for different ranges of a. So we have the derivative. We just plug in our x1, which is equal to 0, into our derivative. So we have 3 times 0 squared minus 4 times 0 plus 1 minus a. So we're going to have 1 minus a. Okay, so now we're going to try different ranges of a. Let's try when a less than 0. Observe that when we do for f prime of x1 for 1 minus a, if a is less than 0, then definitely this entire thing would be greater than 0. So we know that x1 x1 equals 0 is unstable when a is less than 0. Now let's check when a equals 0. We just plug it in for x1. We plug a equals 0 and x1 equals 0. So we're going to have our answer will equal 1, which is greater than 0. It shows that x1 is unstable when a equals 0. Now let's check in between 0 to 1. Between 0 to 1, we get, again, if a is between 0 to 1, 1 minus a would still be greater than 0 since it's still less than 1, right? So x1 equals 0 is unstable when a is between 0 to 1. How about when a equals 1? Well, plug it in once again, and we'll get a 0. Now, this is not greater or less than 0, it's equal 0, so this is kind of inconclusive. So we're going to have to find a different method when a equals 1 for x1 is equal 0. So let's try to approach from the left side. So limit as x approaches 0 from the left, we get a negative solution. And limit as x approaches 0 from the right, we get negative. So solutions approach from one side and move away from the other side. This is called being semi-stable. So we can see that x1 equals 0 is semi-stable when a equals 1. How about for when a greater than 1? Well, for f prime of x1 equals 1 minus a, well, it's less than 0. We finally have an answer that is asymptotically stable. And that's when a is greater than 1 for x1 equals 0. So to summarize, we have a less than 0 is unstable. Oh, this is for x1 equals 0, by the way, or x is 0. A less than 0 is unstable, a equals 0 is unstable, 0 to a is between 0 to 1 is unstable, a equals 1 is semi-stable, and a greater than 1 is asymptotically stable. So that is the summary of the stability for x1 equals 0.
So now we're going to look at when x is equal to 1 plus root a. Subbing x2 into the derivative, we get 2 root a plus 2a. So now we will examine this x for different ranges of a.
When a is less than 0, there are no real solutions.
When a is equal to 0, we get that 2 times root 0 plus 2 times 0 is equal to 0. Therefore, x2 is inconclusive by the first derivative when a is equal to 0. Therefore, we need to take the limit of both sides, and we get that they're both positive. Therefore, x2 is semi-stable when a is equal to 1. Now let's look at when a is between 0 and 1. When a is between 0 and 1, we get that the derivative is equal to 2 root a plus 2a, which is always positive because a is always positive. Therefore, we get that x2 is stable, or it's unstable, when a is between 0 and 1. Now, let's look at the case when a is equal to 1. Subbing that into our equation, we get 2 times root 1 plus 2 times 1, which is equal to 4, which is always positive. Therefore, x2 is unstable when a is equal to 1. Now, looking at the case when a is greater than 1, we get that x2, f of x2 is equal to 2 root a plus 2a, which is always greater than 1 as a is always positive. Therefore, x2 is unstable when a is greater than 1. And here we just have a summary that when of x of the equilibrium solution, x2 is equal to 1 plus root a. It's not real when a is negative. It's semi-stable when a is equal to 0. It's unstable in the range of a from 0 to 1. It's also unstable when a is equal to 1. And it's unstable when a is greater than 1. Now we look at the equilibrium solution. x3 is equal to 1 minus root a for different ranges of a. First, we sub this into our derivative and we get that f of x3 is equal to negative 2 times root a plus 2a. And we can see that when a is negative, we don't have any real solutions. Or x3 is not real when a is negative. When a is equal to 0, we get 1 minus 0, which is 1, which is the same as x2. And we found that when x2 is equal to 1, it's semi-stable, and therefore x3 is also semi-stable when a is equal to 0. Now, when a is between 0 and 1, we get negative 2 root a plus 2a, which is always negative. So x3 is asymptotically stable when a is between 0 and 1. Now, we will look at when a is equal to 1. when a is equal to 1, we get that x3 is equal to 1 minus 1, which is equal to 0. And earlier, we found that when x1 is equal to 0, it's stable, or it's semi-stable. Therefore, when x3 is equal to 0, it's also going to be semi-stable. So we conclude that x3 equals 0 is semi-stable when a is equal to 1. Now, when a is greater than 1, we get negative 2 times root a plus 2a, and that's always going to be positive. Therefore, x3 is going to be unstable when a is greater than 1. So here's just a summary of x3. We get that it's not real when it's less than 1 or when it's less than 0. It's semi-stable when it's equal to 0. It's asymptotically stable when it's between 0 and 1. It's semi-stable when it's equal to 1, and it's unstable when it's greater than 1. And by it, I mean the value of a.
Now that we have found all the equilibrium solutions, their stability, for the ranges of A for which they are valid, we can sketch the phase portraits corresponding to all valid ranges of A. When A is less than 0, there is only one equilibrium solution, x is equal to 0, which is unstable, which means that solutions move away from x is equal to 0 in both directions. X is equal to 1 plus root a and x is equal to 1 minus root a are not equilibrium solutions when a is less than 0 because they are not real. When a is equal to 0, there are two equilibrium solutions. There is x is equal to 0, which is unstable just as before, and there is x is equal to 1, which is semi-stable, meaning solutions approach it from the left and move away from it from the right. When a is between 0 and 1, there are three equilibrium solutions. There is x is equal to 0, which is unstable as before. There is x is equal to 1 minus square root a, which is stable, which means solutions approach it from both sides. And there is x is equal to 1 plus square root a, which is unstable, meaning again, solutions move away from it from both sides. When x is equal to 1, there are two equilibrium solutions. There is x is equal to 0, which is semi-stable, meaning solutions approach it from the right and move away from it from the left. And there's x is equal to 2, which is unstable, so solutions move away from it from both sides. Finally, when a is greater than 1, there are three equilibrium solutions. X is equal to 1 minus square root a is unstable, solutions move away from both sides. X is equal to 0 is stable, solutions approach from both sides. And x is equal to 1 plus square root a is unstable. Solutions move away from both sides. Now, we can sketch the bifurcation diagram, and then, from the diagram, determine the values of the parameter a for which bifurcations occur, and classify those bifurcations. To sketch our bifurcation diagram, we're going to be plotting our equilibrium solutions versus the parameter a. We are going to use dotted lines to indicate when the solutions are unstable, and full lines to indicate when they are stable. We are going to use a different color for each of our three equilibrium solutions. Green for x1 is equal to 0, red for x2 is equal to 1 plus square root a, and blue for x3 is equal to 1 minus square root a. We can use our phase portraits to help us decide when our equilibrium solutions are going to have dotted lines or full lines based on whether or not they are unstable or stable in the phase portrait. We can see as an example that x1 is equal to 0 has dotted lines, it is unstable when a is less than 1, and it has full lines and is stable when a is greater than 1. We can notice once doing our diagram our two bifurcations in our bifurcation diagram. These occur at a is equal to 1 and a is equal to 0, both of which are saddle node bifurcations. This is because they represent critical thresholds between different equilibrium solutions. A is equal to 0 is a threshold between x2 is equal to 1 plus square root a and x3 is equal to 1 minus square root a. A1 is a threshold between x1 is equal to 0 and x3 is equal to 1 minus square root a. There is a change in stability before and after these bifurcations as well.